I almost forgot about the concavity here. So working on this right here, there are no places where this is equal to 0 because 14 can't be 0. So that can't happen. But is there anywhere this does not exist? And the answer is yes, at x equals 2. Now, although this isn't a critical number from the first derivative because it doesn't exist in the function either, and it can't be an inflection point because the function doesn't exist there, it could be a place where the concavity changes. So I just want to double check that right here for the concavity. Is there a change in concavity? So we think about the value 2, we're going to pick a number on each side. So maybe I'll pick 0 on this side, and I'll pick, say, 3 on this side. So I want to know, what is f double prime of 0? Well, if we plug in 0, we get -2 cubed, which is negative. Positive over negative is negative, so that means the graph should be concave down. Now, we're not guaranteed a change in sign on the other side. We have to look to see what happens if we plug in 3. Well, you can only plug in the bottom. 3 minus 2 is 1, which is positive. Positive over a positive is a positive, so it must be concave up over here. And that matches what we saw with the first derivative, that we were increasing on one side of that critical number, decreasing on the other. So there's my concave down. And on the other side of the asymptote, we were decreasing on one side and increasing on the other. So there's that concave up shape. So that second derivative confirms what the first derivative was telling us about this function, that this function does indeed do something like that on each side of its asymptote. But there is no inflection point because f of 2 does not exist. Right? If we plug in 2, we get 0 on the bottom. Does not exist. So no inflection point, but we do have a change in concavity. And the graph reflected that when we checked it.